Alright, so welcome to my talk called Analyzing Kony Mobile Applications. I'm Terry and I'm a security consultant at Centurion Information Security. And here are some of the places you can find me online, such as my blog post or my GitHub account. The agenda for today will look at what is Kony and some of the problems that you might have if you're trying to analyze a Kony application. So we'll look at how does Kony work internally, as well as some of the tooling that I wrote to solve some of the problems that you might have. So just a disclaimer, this is not a talk about security vulnerabilities in the Kony framework. It's more about understanding how the framework functions. So if you're doing a pen test, for example, on a Kony application, you're able to effectively understand what it's doing and how to debug it, for example. So what is Kony? Kony is a cross-platform application development environment. And the idea of Kony is that you can write a single code base and you can generate applications for different platforms like Android, iOS, even Windows 10. But it's most commonly used for mobile applications. So that is where you'll most likely run across it. And like all modern frameworks, it involves the use of JavaScript. Licenses for Kony are relatively expensive. So I took a look at Kony's pricing page on their website, and the public price is $2,500 USD a month. As a result of that, their client base mostly consists of banks and other large corporations. And they have a very helpful featured client page. You might recognize some familiar names, including a few banks. So what are the problems you might have if you're looking at a Kony application? So when I first took a look at Kony, I tried all the standard reverse engineering tooling. So if you think about how you might do security analysis on an Android app, you might decompile the APK file and you look at the Delphic bytecode. You want to decompile it to something more readable like Smiley code or Java. For an iOS application, you might extract the macro binary from the IPA file and you might throw it into a decompiler like IDA Pro, Hopper, or Binary Ninja. You might want to do some dynamic analysis through runtime hooking using tools like Frida, Objection, or Expose, which for any one of you who have done a mobile pen test should be very familiar to you. However, this workflow does not work for applications written with Kony, mainly because the application logic of the application is not contained in the bytecode or the macro binary. The screenshot here I have is a JetX decompiler output of a production build of an app that I pulled from the Play Store. And you might notice some familiar classes like the build config or the R class that contains pointers to your application assets. But there is no classes or methods and so on that actually contains the business logic of your application. So when I started looking at Kony, I looked at some of the past research that other people have done because I did not want to reverse engineer the framework if I didn't have to. So what I found was that there were one blog post and one talk about Kony. And for Kony versions less than 6.0, there's a blog post by NCC Group. And what they found was that the application code for that version of the framework is written in Lua. So if you extract that file from the APK file and you pass it through a Lua decompiler, you will be able to extract source code in clear text and you can read it. For Kony version 6.0 onwards to the latest version of Kony, there was a talk by a guy called Chris Whedon at one of the Black Hats in 2015 entitled Deconstructing Kony Android Applications. And what he found was that for Kony version 6.0, and this is true up to the latest version of Kony, the application code is written in JavaScript, and it's actually stored encrypted in your IPA file or your APK file. And he came up with some tooling to extract that source code from an application, but what I found was that later versions of Kony framework made his techniques obsolete because of some changes. So I extended upon his research and came up with new tools and techniques for that. And this will be the focus of the talk today. So how does Kony work? The first thing that you might want to know is what version of Kony is used to build the application. And you can get that information from a file in the APK called pluginversions.properties. And that file contains the version strings of all the Kony related tools, plugins, and integrations used to build the application. And the version is important because Kony constantly changes. So if you have a technique that works on one version and does not work on the other version, it's probably because there was an update in between that broke something. And this is a sample output of the plugin versions file. I've highlighted the relevant line in yellow, which is the version of Kony Studio used to build the application. And Kony Studio is the name of the Kony IDE, the Integrated Development Environment. And the application source code is in a folder, the assets.js folder of the APK file. And you might see a few different files in there. Two of them, the common jslibs.kfm and the worker-threads.kfm are more or less like the Kony standard library, and they'll be found in every single application built with Kony. And the startup.js file is where all your code specific to the application, so your business logic, for example, this is where it will live. So I started reverse engineering the framework, and what I found was that when a Kony application starts up, it actually loads a shared library called Kony JSVM. So if you decompile the Delphic bytecode of the APK, you will see a method that calls system.loadLibrary, and it loads the Kony JSVM shared library. And there will be a different shared library for every CPU architecture that the application is meant to support. So if the app is meant to support x86 and ARM, you'll see two different versions of that shared library. And the shared library contains symbols that indicate the use of the V8 JavaScript engine. So this is just a very tiny subset of all the V8 related symbols in the shared library. And the entire JavaScript engine is actually statically compiled into the Kony JSVM library. And there is an interesting function in that shared library called Kony JSVM load files to VM that is called during the startup process. And it is only called once when the application is launched. And the function does three main things. First, it derives the decryption key for the source code. It decrypts the source code. And finally, it loads the decrypted code into the V8 engine. If you want to pull out the source code, you want to decrypt it, it's important to know what the key derivation logic is. So how does the application know, or how does it derive the decryption key used to decrypt the source code? And that logic is stored in the Kony JSVM load files to VM function. And the first thing it does is it allocates 256 bytes of memory with the memset function. Next, it calls a function called getTime. And with the return value of the getTime function, it throws it into a char XOR function before appending the return value of that to the allocated block of memory. It then does the same process, but with another function called the getEnd function. And finally, it calls a function called getPackageName, and it throws it into a different char XOR function before appending that value into the allocated block of memory. Once the key derivation is done, it will finally call a simple SHA-256 function to hash all the allocated block of memory into a single 256-bit key that is used for decryption. You might be interested to know what the three different functions that it called during the key derivation process are, and they are actually Java functions that are in the Delphic bytecode. So the native code in the Kony JSVM shared library calls out to some other function in your APK file. And the first function that it calls is the getTimestamp function, which base64 decodes a VM_FY string that is actually var base64 encoded. So it uses that string as a key value and reads it from a application.properties file. And that key actually contains the timestamp value of when the APK file was built. So if you have the same APK and you built it twice, the decryption key will be different for each time. The next function, the getName function, calls Android's context.getPackageName method, which returns the package name of the Android application. For the binary, the APK file that I was analyzing that I pulled from the Play Store, the package name is com.kony.functionPreviewApp. And finally, the getEnd function reads the app ID key from the same application properties file. And that key contains something called the Kony app ID of the application. And this is probably something that is different for every Kony application. So this is an example of the application.properties file. It's a bit small, so I blew up the relevant section. And you'll see that the app ID in this case is fpapp, and the var key contains the Unix timestamp of when the application was built. Now that we know how the decryption key is derived, the final piece of the puzzle we need to decrypt the source code is the actual algorithm that's used for encryption and decryption. I was unable to identify the specific algorithm from the shared library, but I found hints that boring SSL was statically compiled into the shared library. So it turns out that we need to look somewhere else, and that somewhere else is actually a Kony_loadfile.exe executable that was used during the build process. The Kony visualizer IDE uses that executable to encrypt the source code before packaging it into the APK file or the IPA file. And the interesting thing is that we can pull the executable from the installer, so the installer is freely available online for download. You can't actually use the IDE to build anything without a valid license key, but you can extract files from it for analysis. And the decompiler output of that executable shows that the encryption algorithm in use is AES-256 in CBC mode. In the Kony_loadfile.exe executable, there is a call to OpenSSL's EVP encrypt init function. And the fourth argument of that function specifies the initialization vector of the encryption process, and it points to the .data section, which contains a string ABCD1234 EFGH 5678. So that is most likely the initialization vector used during the encryption process. And we found the same string in the Kony load files to VM function in the shared library. So it's very, very likely that that is actually the IV. So when it comes to writing a decryptor, Chris Whedon actually had an idea in 2015 to turn that Kony_loadfile.exe encryptor into a decryptor by binary patching that executable. For older versions of OpenSSL, you initialize the encryption routine by a cipher_init_ex function that has a single parameter that takes an integer that decides whether it's used for encryption or decryption. So what he did was he binary patched a single byte in that executable, and you can now use it to decrypt the source code instead of encrypting it. However, this no longer works for newer versions of Kony because updates to that executable makes use of a newer OpenSSL API, which has separate encryption and decryption functions. So you can no longer just binary patch a single byte in the executable to turn it from an encryptor to a decryptor. So we have to re-implement everything from scratch ourselves. I had a few ideas of how to do it. The first potential option is to just rewrite the whole key derivation algorithm in Python or a different programming language. But this is actually very tedious to do because you have to get all these specific steps right. And it is quite brittle, as if they update the framework to change the algorithm slightly, you have to rewrite the whole thing. And the key derivation process actually mixes in a secret value that's unique to each version of the Kony framework. And if you want to statically extract that key data automatically without human analysis, it will take quite a bit of effort. The second option I came up with was to pull the derived key at runtime from the actual application that you are analyzing. So this is quite simple to do with a debugger or a dynamic binary instrumentation framework. It's relatively simple to implement, and this is the approach that I eventually ended up with. The third option that I did not actually implement, but it's interesting to consider, is that you can just emulate the key derivation routine. So I think Alice mentioned the Unicorn emulator earlier. It's fantastic. It's actually very simple to use the Unicorn emulator to emulate that key derivation process. You just have to substitute in the calls to the Java functions. This is a very useful option to keep in mind if the application that you are analyzing has a lot of anti-debugging mechanisms in place, which makes it a bit more difficult if you want to attach a debugger or a DBI. When it comes to the implementation of the decryption routine, I decided to make use of Frida, which is a dynamic binary instrumentation framework. If any of you have done mobile application analysis, you would most likely be familiar with Frida. It gives you the ability to do things like attaching to functions. You can dump memory from the running process, and you can even like modify runtime behavior. And the goal is to write a Frida script to attach to a point in your key derivation process and to dump the decryption key when it's done. So looking back at the key derivation process, it appears that the simple SHA-256 function is the most appropriate location to hook, because that is when the key derivation process is completed. And the third argument to that function is a pointer to where the output of the hashing function is written. So we can just hook that function and extract 32 bytes from it when the function is done running. And this is the core of the Frida script that I ended up with. You can see in the first line that I highlighted, we are attaching to the simple SHA-256 function in the shared library. In the second line, we are telling Frida that we want to hook the third parameter to that function. And on the third line, once the function is done executing, we are telling Frida to dump 32 bytes of memory from that pointer address and return it to us. After dumping the key, we can write a Python script to decrypt the application source code. One complication I ran into was that older versions of Kony, instead of the ABCD 1, 2, 3, 4 IV that I found, was actually using all zeros for the IV. However, this is quite simple to get around because you can just try both IVs and see which one results in a valid decryption. And this is especially easy to do because the decrypted output is supposed to be a zip file. So all we have to do is run the decryption process and we check the first few bytes of the output. If it matches the magic value of a zip file, we can just say that the decryption is successful and we can stop. Otherwise, we just try the other IV. So for my first demo, I'm going to be showing the decryption script running. All right. So you can see on the right side, I have my Android device running, so I'm running the application. So on the left, I have the terminal where I'll be running the decryption script. So I wrote a script called unpack.py, which will launch the application, pull out the key, and decrypt the source code. And it takes 3 parameters, which is the APK file, the package name of the application, and the output directory of where the decrypted source code will be written to. So you see that I launched the application, I extracted the key, and I decrypted the source code. And there are 3 files in the output directory, and they're all zip files containing JavaScript source code. If we unzip one of the zip files, we will see a bunch of JavaScript source code, and that is where all your business logic of the application lies. So just to confirm that the decryption process is correctly done, we can open up any of the JavaScript files, and we will see the source code of the application in clear text. Right, so that's how you extract source code from a Kony Android application. However, I wanted something more, because I wanted a runtime debugger. And the reason for that is, if you want to go through a source code of a foreign application, it's not really fun, especially if the application is very large. If you have a runtime debugger for that framework, you can make your analysis very easy by giving you the capabilities like setting breakpoints. You can monitor when a variable value change, and you can even like modify how a function is implemented if you want to bypass some behaviors. The first option that we have for a debugger is we can of course use GDB. You can attach GDB to a running application on Android, and you can analyze the native instructions that are running. However, this is not very ideal because there is no good way to map a series of, for example, x86 instructions into a line of JavaScript code. So you actually lose the semantics of the application when you're debugging it that way. Looking at the Kony documentation, so like all decent development environments, the Kony IDE offers debugging capabilities. And you can access those capabilities if you build the application in debug mode. And the interesting thing here is that Kony uses Chrome DevTools as their official debugger, which suggests that the debugging capabilities are implemented with your standard V8 functions instead of something more custom. So at this point, let's take a detour into a quick history lesson of V8 debugging. V8 initially contained a debug API that started a remote debugging service on a TCP port. So there was an enable agent method, and if you call that method, you will launch a TCP service listening on a port that you specify, where you can connect to it and debug the application. This agent was eventually removed in later versions of V8, and from what I found from the V8 mailing list, the justification appeared that V8 did not want to ship TCP-related code because they do not want to maintain code for a specific platform. If you think about a TCP service, it will be slightly different for Windows, Linux, and macOS. And V8 wanted to leave it up to the consumers of the JavaScript engine to implement that. So consumers of V8 implemented code that imitated the behavior of the old remote debugging service that was removed. And this was mostly so that your existing debuggers will continue to work. For example, Node.js did something like this, where they implemented some custom code that essentially did what the old debugging service did. And this debug API in later versions of V8 was actually removed in favor of a new inspector API with more capabilities. And this inspector API is what Chrome DevTools in a current version of Chrome uses. So how is this relevant to what we want to do, which is a runtime debugger for Kony? Kony uses a version of V8 that does not support the new inspector API. So if you look at all the V8 related debug functions, you will notice methods from the debug namespace instead of the inspector namespace. So Kony is probably implementing like what Node.js did. They implemented the same remote debugging service over a TCP port. And the problem was that I could not find any traces of that code in the release build of the shared library. So after looking at the build process of Kony further, what I found was that when a Kony application is built in debug mode, everything else in the application is the same, except that a different shared library is packaged in. And if we pull out the two different shared libraries from the installer, we can do analysis to see like what is the difference between the two. So if we binary diff the two shared libraries, so we can use a tool like bindiff or diphora. So this is what I did, and what I found was that if you want to do this, you need to diff the shared library from the same version of Kony to avoid any noise from, for example, Kony implementing new functions. So what I found was that the debug shared library contains several methods from this JS debug agent family of functions that actually implements the remote debugging service. And the interesting thing is that the JS debug agent functions are actually JNI functions, which means that they have a corresponding Java class so that the APK can call it. And this Java class is actually the JS debug agent class. And that class is still present in the Delvik bytecode of a release build of the application. So this is what the class will look like, just a very small snippet of it. And you might notice that there is a port, there's a variable called port, where you can specify which port you want the debugger to be listening on. So at this point, once we know all of this information, we have a game plan to get a debugger running for a release build of Kony. What we can do is we can repackage the APK file with the debug version of the shared library because everything else about the application remains the same. We can then use something like Frida to hook the JS debug agent Java class to enable the debugger. So once we've done all of that, we should then be able to connect to the application using Chrome DevTools. So there were a few problems that I ran across along the way. The first was that we cannot just call the JS debug agent Java class from the main thread of the application because it needs to run in the background. Otherwise, your application will just be stuck there. So there's already code in the Delvik bytecode that does this. So all we have to do is we have to find it and we have to call it. And the method that we are interested in lives in a class called Kony main. However, there's a different name on every build of Kony due to product obfuscation. So you have to do some manual analysis to find out which is the method that you need to trigger. So what we want to look for is we want to look for a method that returns a handler object. And in that class, there should only be one of such methods, so it should be relatively easy to identify. Yeah, so this is the JetX decompiler output of the class, and the method n is something that is what you should be looking for. So as you can see, it returns the handler object, and there will only be one of such methods in that class. So as usual, I wrote a Frida script, and for this script, you have to modify the method name that you want to call, because like I said, that will be different for every build. In this case, we are calling the n method, and we are telling it to listen on port 9222. So the Frida script actually runs the debugger on port 9222. However, the problem that I found was that I was still unable to connect to it using Chrome DevTools, because like I mentioned earlier, the newer versions of Chrome DevTools uses the new inspector API instead of the old debug API. So when the Kony IDE actually launches this process, they probably have some code in place to bridge between the two different APIs. Initially, when I first ran across this problem, I thought that I have to implement that bridge myself. But what I found was that Visual Studio's Code debugger actually supports that old debugging protocol, which is most likely because they wanted the ability to debug older versions of Node.js. And this saves us the work of re-implementing the bridge. And we can configure Visual Studio's Code debugger to use that legacy protocol using a launch.json config file. So something like this. And what you can see is that I'm telling the Visual Studio's Code debugger that I want to connect to port 9222 and use the legacy protocol. And once the debugger connects, you will see something like this in your Visual Studio's Code, which I will show a demo of now. So the first thing that we need to do is we need to repackage the APK file with the shared library. And I wrote a patch debug script to do that. And it takes in the APK file, the shared library, the debug version of the shared library, and the name of the output APK file that you want to write to. So I'm writing to a file called mod.apk, and it will take a while to run because you're repackaging the entire application. And once you've repackaged it, you will need to sign it to run it on an actual Android device. And yep. So now I will install the new APK that I've created into my Android device. Right, so once we've installed the application, we can ensure that it actually runs properly. So, yep. Yeah, so the application is now running. So the next thing I'll do is I will use my Frida script to activate a debugger. And once that script runs, you will notice that the application will pop up a message saying that waiting for debugger to connect. Right, so now the application is waiting for a debugger to connect to it. So the next thing that you need to do is you need to port forward the listening port from the mobile device to your host machine. And you can do that using ADB forward, which is what I'll be doing now. So I'm port forwarding port 9222 on my mobile device to 9222 on my host machine. And when I click the debug button, I am connected to the Android application. So you see that the message is now gone and you can use the application like normally. So with a runtime debugger, you can do things like, of course, you can look at the source code of the application when it's running. You can have capabilities like attaching breakpoints to places in the code that you're interested in. So I'm setting a breakpoint on that particular line. You can actually tell the debugger that you're interested in certain variables and you want to monitor what values they have. Yeah. And you can even modify what a function is doing. So if you want to patch out certain security checks or you want to bypass, for example, SSL pinning, you can just edit the function when it's in the application. All right. So everything I've shown up to now is for Android. So there's of course another platform that we are interested in, which is iOS. And for iOS, I did not want to have to reverse engineer everything from scratch. So my logical assumption was that the implementation should be very similar to what Android is using. So I started looking for references to cryptographic functions in the macro binary. And what I found was that there were several references to the common crypto family of CC crypto functions. For those of you unfamiliar with macOS or iOS programming, common crypto is Apple's standard library for cryptography. And after I started doing some tracing and debugging on the application, I found that the CC crypto family of functions were called when the application starts up, which is a very strong indication that that is actually the method used for decryption. So similar to what Android is using, the JavaScript source code is encrypted with AES-256 in CBC mode, but the difference is that the IV appears to be different for every application. So on Android, you have the static ABCD 1, 2, 3, 4, so on IV, but for iOS, the IV is different for every application. So what we need to do is we need to pull out that IV alongside the key when we are doing it with Frida. And we can write a Frida script to hook CC crypto create that particular function and extract the key and IV from the function arguments. So this is the function definition from Apple's documentation, and you can see where the key and IV parameters are. So like my Android implementation, I wrote a Frida script for iOS. On the first line that I highlighted, I am attaching to the CC crypto function. In the second line, I am extracting the IV from the fourth parameter, and in the third line, I'm extracting the key. So just a demo. So the script is actually exactly the same function parameters, arguments as the Android version. It takes the IPA file, the name of the package name of the application, and the output directory that you want to write the results into. So I am running the script now. And you can see that I've extracted the IV and the key from the application. And if I look at the JS files directory, there will be a single zip file in there that contains the application source code of the IPA file. If you unzip it, you will see a bunch of JavaScript code. And if we open one of the files, it'll be in clear text. Yep. So for the debugger situation, I was not able to come up with a working debugger for iOS because Kony on iOS uses the JavaScript core engine instead of the V8 engine. So I couldn't quite figure out how to get a debugger working. However, I figured this was actually good enough for most situations because your application logic should be exactly the same as the Android application. Because the promise of Kony is that single code base, you can generate the same app for multiple platforms. So aside from maybe some platform-specific interactions, like biometrics, for example, the application logic should be exactly the same between the two applications. So in conclusion, we've covered the Kony mobile application startup process. We've shown how to extract application source code from your APK file or your IPA file. And we've shown how to debug a Kony Android application. All the scripts I've shown today are available on GitHub. So if you're actually doing analysis on Kony, you can just run them. The Android debugger script does not ship with the required version of the lib Kony JSVM shared library. You'll have to extract that from the installer yourself, but you can just download the installer from Kony's website. And just a few random thoughts to close out the presentation. There are a lot of new mobile frameworks coming up that's not using your native development environments. So you have things like Apache, Cordova, or React Native. And your standard application analysis method or tooling will probably not work on those frameworks. So tooling needs to be written to keep up with changes in the development environments. And if you're looking at mobile applications, it's useful to have very basic reverse engineering skills, especially for Android if you're looking at native functions, or iOS, your entire application is actually just a macro binary. So, yep, the GitHub link for where the scripts can be found, and questions? Yep. Yes. Yes.
So the IV in the Android app was static, right?
Yes.
But was it dynamic? In the iOS version looked like dynamic.
So it's still static in the sense that the application has the same IV each time, but it's different for every build of a iOS application. So if you're analyzing two different iOS apps, the IV will be different.
For the iOS, but not for the Android app?
Yes, so for Android, depending on the version, they will either have the all zeros or the ABCD IV.